This is another important topic that's been discussed quite a bit actually once the issue was raised that it's not just the temperature with global warming, temperature increases that we have to worry about. In fact, we have to worry a lot about the increase in humidity as well, because there is the moist heat stress that human body can tolerate up to some extent, the dew point temperature. What happens essentially, warming, the first order effect is that humidity will increase because a warm atmosphere is a thirsty atmosphere. And even in the deserts, you expect overall with global warming, the humidity is going to go up. And body's ability to cool down by sweating is going to be limited as the humidity in the air around begins to increase, because it's the difference in the humidity of the air, specific humidity versus the body's temperature that's going to determine how much evaporation can happen from the body itself, right? Greatly enhanced risk to humans as a consequence of empirically determined lower moist heat stress tolerance. What's the lowest wet bulb temperature we can tolerate, beyond which heat stress becomes a killer, right? So the PNAS articles give you this significance for general public, lay audience. Increased heat and humidity potentially threaten people and societies. Here we incorporate our laboratory measured physiologically based wet bulb temperature thresholds across a range of air temperatures and relative humidities to project future heat stress risk from bias corrected climate model output. So many details there. Basically, climate models are making projections into the future based on various scenarios, or you can just focus on warming thresholds of 1.5 to 3 degree, 4 degrees C and C, and try to compute how the moist heat stress will keep going up, or how the wet bulb temperature will keep changing. And they do some regional calculations as well as we see it. And the projections, typically models have biases, so they do some bias correction, which is a statistical based past data, relying on past data to correct the model's systematic biases to get a better estimate of the future. These vulnerability thresholds These vulnerability thresholds substantially increase the calculated risk of widespread, potentially dangerous, uncompensable humid stress. Some of the most populated regions, typically lower middle income countries in the moist tropics and subtropics, violate this threshold well before the 3 degrees C warming level. So if we keep warming, and we are pretty much going past 1.5 now, and also maybe 2 degrees C, unless we really wake up and find lots of solutions, start pulling out CO2 from the air like Coca-Cola or other greenhouse gases as well, and do a lot of the adaptation mitigation solutions as well, as I'll allude to later in the paper. Further, global warming increases the extent of threshold crossing into drier regions, for example in North America and the Middle East. These differentiated patterns imply vastly different heat adoption strategies. Limiting warming to under 2 degrees C nearly eliminates this risk. So another way to push for this 2 degrees C warming threshold. So that's the summary for the lay people. So let's read the technical abstract. As heat waves become more frequent, intense and longer lasting due to climate change, the question of breaching thermal limits becomes pressing. A wet bulb temperature TW of 35 degrees C has been proposed as a theoretical upper limit on human abilities to biologically thermoregulate, cooling by sweating. And if you don't know what is wet bulb temperature, basically you have a thermometer which is measuring the temperature around, but it doesn't account for impact the heat stress, moist heat stress. So if you put a wet cloth around the bulb of the thermometer, then that measures the wet bulb temperature literally, because that includes the energy you need for evaporating from that wet moist towel. But recent empirical research using human subjects found a significantly lower maximum TW at which thermoregulation is possible even with minimal metabolic activity. Projecting future exposure to this empirical critical environmental limit has not been done. Here, using this more accurate threshold and the latest coupled climate model results, we quantify exposure to dangerous, potentially lethal heat for future climates at various global warming levels. We find that humanity is more vulnerable to moist heat stress than previously proposed because of these lower thermal limits. Essentially, the previous estimates were not as physiologically robust as this study here. Still, limiting warming to under 2 degrees C nearly eliminates exposure and risk of widespread uncompensable moist heat waves, as a sharp rise in exposure occurs at 3 degrees C of warming. Parts of the Middle East and the Indus River Valley experience brief exceedances with only 1.5 degrees C warming. So even the lowest of the levels we are dreaming about can provide exceedances in some places like the Middle East and the Indus River Valley, which is Pakistan, India, Northwest India, and so on. More widespread but brief dangerous heat stress occurs in a plus 2 degrees C climate, including in Eastern China and Sub-Saharan Africa, whilst the US Midwest emerges as a moist heat stress hotspot in a plus 3 degrees C climate. In the future, moist heat extremes will lie outside the bounds of past human experience and beyond current heat mitigation strategies for billions of people, while some physiological adaptation from the thresholds described here is possible. While some physiological adaptation from the thresholds described here is possible, additional behavioral, cultural, and technical adaptation will be required to maintain healthy lifestyles. So let's assume everybody's lifestyle standards of living go up, everybody gets an AC, then air conditioners have to have coolants which are not harmful to the environment as they are now. HFCs, HCFCs are very strong greenhouse gases, and that everybody working outside also, let's say, has some fabric with a chip that can cool them, etc. So you can imagine all kinds of science fiction kind of futures, but you want to prepare for the worst case scenario as well, assuming that we will not always be protected from the moist heat stress. So prior thresholds underlain by physiological theory set the upper limit of the human body's adaptability to extreme heat at a wet bulb temperature of 35 degrees C, also popularly referred to as the human adaptability or survivability limit. TW is a measure of the moist enthalpy in the atmosphere and is thus thermodynamically equivalent to other proposed moist heat stress measures, but has a longer history and simpler physiological interpretation. Dating back to Haldane's pioneering work, TW has been a useful measure in the description of human heat stress, as a sweat-covered human body acts much like a wet wick of a wet bulb thermometer. Given the optimal human core temperature is 37 degrees C, an internal thermal gradient conducive to moving metabolic heat from the core to the periphery of the body via skin blood flow would stipulate that skin temperature must remain below a maximum temperature of 35 degrees C. Okay, so 37 degrees C core temperature is now argued to be different, but let's not worry about it. When the ambient environment reaches TW of 35 degrees C, the body would be no longer able to thermoregulate via conduction and convection of heat brought to the skin via blood flow or evaporation of sweat on the surface of the skin. Importantly, Sherwood and Huber stated that this was an upper bound and proposed that a lower number would be more realistic, but an exact lower estimate was not estimated. They found the warming above this threshold did not become widespread and persistent unless global warming was above 6 degrees C. So this paper looks at the physiological limits in a better way, as well as reduces the threshold where we will meet the limits of human body's moist heat stress tolerance. Okay, so some figures they show, again remember there are uncertainties in the projections, they have done bias correction, but in general models are better at doing temperature at regional scales like India scale and not at regional or local scales like a city level, but many techniques exist for downscaling, and then you have to worry about thermodynamic response in terms of humidity, which depends on dynamic response, which is wind changes, because often moisture comes from somewhere else. For India, it could come from the oceans, and there are nice studies showing how heat waves themselves depend on where the source of heat is, whether it's a wave, whether it's advection, whether it's nearby ocean, land, etc., etc. So keeping all this in mind, we are looking at global warming target here going from 1 degree, which we have already crossed, to 4 degrees, and you are looking at cumulative exceedances in terms of persons, billions of people being exposed to moist heat stress. So annual hot hours under 1.5, 2 degrees C and 3 and 4 degrees C limits. So you are looking at the global picture here, and this is population, which is tricky in terms of exposed population, so I don't want to deal with it too much. So population projection in 2050 following the shared socioeconomic pathway 2. I won't say much about it, but I have elsewhere podcasts in details on what the shared socioeconomic pathways are, which were used in the recent IPCC assessment. And there are population projections which are also tricky because fertility rates are dropping everywhere and women are not having children even when the government promises to pay them, and so on and so forth. But keeping all that in mind, what do you want to do with these? As annual hot hours increase with warming in expected places, right? The Himalayan foothills, the Indus Valley region here, eastern China, Sahara, and eastern seaboard of the US, and so on. What are the risk mitigation measures you can take? What are the adaptation measures you can take? And what information do you need at what scale to invest in future mitigation adaptation? You cannot invest everywhere, which means you need very hyper-local information, which I've talked about elsewhere. So this is global person hours of threshold exposure in millions under different threshold scenarios, warming levels, TW limit, and the empirical limit of the people in millions. So obviously as warming goes up, scary number of people get exposed. And looking here at annual hot hours over South Asia and East Asia, North Africa. So we are looking at South Asia, East Asia, North Africa and Middle East, as well as the US, for various levels of warming relative to pre-industrial levels. So this is annual hot hours, and here we were looking at annual hot hours under different scenarios relative to pre-industrial level as well. What is the difference? I should have paid more attention, but yeah, 1.5, 2, 3, 4 degrees, looking at the regional scales. Here we were looking at global scales. Here we are zooming down and looking at regional scales with more details. So the table provides further details. Annual hot hours for major cities in the world. So South Asia, East Asia, Middle East, Africa, North America, you get this countries as expected and cities as expected. Delhi, Mumbai, Kolkata, Chennai, Karachi, Dhaka, Dubai, Aden, Bandar Abbas, Basra, Lagos, and so on. New York, Chicago, Philadelphia should be there as well, and so on. And the question again is, even if you come down to Delhi level and give these various estimates in terms of annual hot hours, what can be done? What kind of investments will be needed? What are the no-regret decisions? Increasing urban green cover will be a no-regret decision, for example, and reducing pollution will be important. And then buildings can be taken care of for reducing energy consumption, as well as heating and cooling that is done to keep people happy. But what about outdoors, and so on and so forth? So very brief, so I'll just jump to discussion and implications. These results indicate that a significant portion of the world's population will experience, for the first time in human history, prolonged exposures to uncompensable extreme moist heat. Humans will struggle to adapt to these conditions in a warmer world, as they will present widespread challenges across many aspects of food, energy, water security, human health, and economic development, including in the world's most populous and most vulnerable regions. The paper talks about how vulnerabilities will change and what they are now and how that will exacerbate exposure and outcomes, etc. Past research focusing on TW 35 degrees C upper limit to human adaptability consistently highlighted the Middle East and South Asia as regions that would experience the brunt of deadly or intolerable conditions, as our study does. We also find that sub-Saharan Africa may be the true hotspot of TW greater than equal to 35 degrees C in the future using our bias-corrected projections. Our research shows that the footprint of life-altering heat using updated empirically derived heat stress limits is vastly expanded. So even North America is showing up here. The additional regions most significantly affected are projected to be equatorial and Sahel regions of Africa and eastern China, given future warming scenarios that reach upward of 2 degrees C. A viable outcome by the end of the century, perhaps sooner, not just by 2100 but maybe before, without drastic reductions in greenhouse gas emissions. So mitigation, no doubt at all. Continued warming above 3 degrees C and 4 degrees C respectively causes North and South America as well as Northern Australia to experience extended period of dangerous heat. These results are another indication of the importance of restricting warming to 2 degrees C as suggested in the ratification of the Paris Agreement in 2015. Here we note the differences between our study and that of a recent publication by Freischet et al. And why this manuscript improves upon the former in terms of the analysis of TW thresholds. Freischet et al. Found that the exposure to TW of 31 degrees C, a statistically derived threshold in their study, was much more widespread than in this study, even at 1.5 degree and 2 degrees C in the Western Hemisphere and at 3 degrees C in parts of Europe. Overestimation of TW in TW are likely accrued through three main factors. One, the use of non-bias corrected CMIP6 data, so not worrying about model biases. The use of daily averaged air temperature and relative humidity to calculate the wet bulb temperature, and the use of Stull's equation to calculate TW instead of Davies-Jones. I didn't go into the details, but you can look up how you calculate wet bulb temperature matters as well. Okay, the latter two methodological choices can each impart a 1 degree C error in the calculation of TW, easily large enough to inflate values of unrealistic values given certain amounts of warming. It's important to note that these TW thresholds were created for a young and healthy population, albeit unacclimatized, doing minimal activity. In other words, even in the US, there are articles arguing about how people can get acclimatized to increasing heat. You have to be careful because there is genetic adaptation. There is some evidence that mortality is much higher in the mid-latitudes to heat waves as compared to the tropical countries where people may be genetically adapted, but acclimatization is something you get used to chronic changes in temperature. So this means that thresholds are certainly lower for those who are more vulnerable to heat, either through age, body size, and morphology, comorbidities, medication use, or any physiological or behavioral impairment to thermoregulatory capacity. Additionally, these thresholds did not take the impact of solar radiation on human thermal balance into account, which will likely also modify thresholds. So it's not just that you're in the shade during this heat stress, you may have direct impact of solar radiation if you're working outside, a vendor outside, or whatever. Thus, some components of the real impact on populations are likely to be underestimated in this study. The increases in heat stress evidenced in the study must lead to changes to daily life and the need for large-scale adaptation efforts to mitigate heat stress risk. However, it's indisputable that serious health complications on a large scale up to and including death will occur where environmental conditions associated with uncompensable heat stress become more frequent and longer lasting unless behavioral or technological interventions are implemented. I jumped a lot of discussion here. It's an inevitable consequence of energy balance that unless environmental conditions are changed, the positive internal heat balance must eventually lead to a heat stroke. One does not need to run those physiological experiments to their unethical conclusions to understand that end results. Beyond the health impacts to the individuals exposed to extraordinary heat, the magnitude to which spillover effects take place is unknown, and questions as to whether these regional climate risks translate into a larger scale climate-induced catastrophe also is not looked at here. It must be the work of multidisciplinary teams of physical, health and social scientists, especially those with specific indigenous knowledge of those who will experience the highest risk of extreme heat due to climate change, to quantify these gradients of adaptability and survivability and provide context for just climate futures for all. So some general statements, but important. So it ultimately comes down to having risk maps at hyperlocal scales. And remember, there are two steps. The immediate day-to-day management of heat waves is a disaster preparation, mitigation is longer term, preparation, prevention, recovery and so on, hydration centers, shelters. But the mitigation efforts are longer term adaptations, as I mentioned, with green roofs, urban greenery, and there is some study by Udit Bhatia who looked at Ahmedabad, looked at heritage sites and argued that green infrastructure, which promises so much mitigation of heat, is actually not as effective as it claims to be. People write other papers just following up these kinds of works which are not as robust, but Udit Bhatia's work is quite robust and shows that green infrastructure right now may not be as effective as we think, so that also has to be pursued in detail. Okay, so I will leave it here, but risks are there. Risks are downscaled to regional scales like Delhi, but even in a city, the risks depend on which neighborhood you are in and what kind of building you live in, what infrastructure you have in terms of hospitals, shelters, hydration centers, and even early warnings. Vulnerability depends on how you respond to early warnings as well. Okay, but disaster management is getting better in India. Heat wave action plans are there at local scales and so on. So let's hope it will be in fact a just transition to warmer climates before we begin to ramp down our emissions and our impact on global warming and so on. So see you in the next podcast.